Hello everyone. So in this video lecture, we're going to see Garay model of blockchain, which is actually a very important model. And you can call it Garay model, you can call it Garay model, whatever goes best with you. You can just call it that, right? Because I too am really sure about its pronunciation. So I think I'll be going with Garay model for all the following slides. And you can just go with anything that you feel its pronunciation is right that way. Let's then start with the blockchain backbone. So, this was actually the first formal theory that was given to explain and prove the security of Bitcoin and the other cryptocurrencies. Until then, Bitcoin was working in practice, but the community did not have a solid, a rigorous model to prove to give answer to the most important, most crucial question that says, why is Bitcoin secure? So interestingly, you know what? This is something that Nakamoto's original Bitcoin paper could not properly answer. It introduced the protocol, but it could not mathematically prove its security. And this gap got filled in 2015 when researchers Juan Guerre, Egelos Kiayas, and Nikos Leonardos they published the blockchain backbone model at Eurocrypt. They provided an actual framework, a rigorous framework model that formalized and tested Bitcoin's core security assumptions. And how it tested, what tested, that is what we're going to study now, and that is what is your Garay model. The same team went further in 2017, published an extended version at Crypto, which revisited, re-strengthened their original model. Because of this, the blockchain backbone is widely regarded as one of the most important works after Nakamoto's original paper because it answered the very most important question, why is Bitcoin secure? And it is considered almost like the second foundation pillar of blockchain research. With this, let's go to the next slide of what a peer-to-peer network of money actually means. So what happens in this type of system, every node or let's say every participant in the network has a copy of the financial state. In simple terms, they all know how much money is there in every bank account, or I would not say bank account, in every account of the person who's there, right? So whenever someone pays someone else, they generate what is called a transaction, and a transaction is nothing. It just says you subtract from this account, add to this account if this account is sending money to this account. Make sense? The transaction is then just broadcasted to everyone in the network, and when the nodes receive it, they update their own records to reflect the change in the balances. Because they have to subtract from one, they have to add into another, right? Now, an important point is that a transaction can only be created by the person who is sending out the money. And how does the system make sure it happens? Because the person who's sending out the money has to, has to append in it their own digital signatures. And without the right signature, the transaction won't be considered valid by the other participating nodes. But here's the most powerful idea, the network is completely decentralized. There's no bank, there's no PayPal, there's no central authority that is going to govern the transaction. All the participants collectively are going to maintain the system's truth. And if you think about it, everything becomes very simple if we just had a central authority like a bank who's managing from where the money is going, where the money is getting into. But the beauty and the challenge of blockchain is that it achieves all of this without needing any central trust. Then coming to the assumption that time is discrete. What this means is that we don't think of time as a continuous flow, but rather as rounds, round one, round two, round three, and so on up to round R. In each round, new information, let's say transactions, can appear and spread and can appear and be broadcasted into the network. We also assume that the network is synchronous. What do you and I mean by synchronous network? That means if an honest participant sends out a message, each node is going to receive it by the next round, that is round R plus 1. In practice, you can think of one round as the amount of time it is going to take for a message to fully travel across the entire network. The assumption helps us to create a simple step-by-step model for how transactions move and they get confirmed in the system. Now let's talk about the role of adversary. So when I talk about the blockchain, when I talk about the Bitcoin, adversary represents the attacker. And here it can be anything. To capture this formally, researchers model it as what? It as an arbitrary probabilistic polynomial time Turing machine, that is PPTTM, probabilistic polynomial time Turing machine. Now, it may sound very theoretical, what is probabilistic polynomial time Turing machine, but just leave that aside. The key idea is we don't need to specify what kind of attacks we are worried about. Instead, the model stays whatever is possible, whatever attack exists as of now, or whatever could happen in the future, the model has to be resilient against all of that, right? The blockchain model has to be resilient against all of that. And that makes the analysis extremely powerful. There's only one adversary in the model, and then that adversary controls all your other nodes, right? But that is the point. You can have just one adversary in the model, but under the influence of this adversary, you can have multiple participants who are going to coordinate with this adversary now. They don't have to do with anything with the other nodes, right? They're all not working independently, but under the influence of this adversary, that is one adversary in the network, right? On top of that, parties under the adversary's control can communicate in any way like they want to during each round, giving them full flexibility to plot against the honest participants. So essentially, the adversary is modeled as being as strong as possible within the network limits, within the computational limits. And if the protocol still holds secure under such a strong adversary, then we can be confident that it's robust in the real world scenario. Now we're telling you about everything that is there assumed in the Garay model. The Garay model said time has to be in rounds. The Garay model says that adversary can be howsoever much powerful, right? It can control now what and how many nodes it can control. Let's just see. First, we're going to talk about the Sybil attack. Now, it's one of the biggest threats in the decentralized systems that says Sybil attack. What does Sybil attack mean? A cyber attack means there's one adversary, but it pretends to be many different participants on the network. They can fake IP addresses, they can fake phone numbers, fake emails, fake Facebook accounts. In short, they can create as many fake identities as they want. So because of this, we cannot rely on the centralized services. We cannot rely on simple heuristics like, okay, take a count of the number of participants to determine who's true. We cannot do that because we have fake nodes in the system who can actually just nullify the honest nodes participation. If we just take a vote, the adversary can just flood out the system with fake identities and completely skew our results. So in our model, what happens? We say there are n parties in total. Out of these, fewer than t are corrupted. So you see, n are the total parties. T, which is lesser than n, are actually the corrupted nodes, and even less than t also can be the corrupted nodes. And corrupted nodes means they're controlled by the adversary. And the remaining n minus t, that is also less than n, obviously, are honest nodes. Each party is, especially the honest ones, the honest nodes of the network, want to publish their own transactions to the network. But new transactions keep coming in during different rounds, and it takes some time for these to travel across the network that defines our round time. And here's the real challenge. How can all the parties agree on which transaction happened first, because the transactions are just coming in? This isn't just a technical detail, it is absolutely crucial for security. Just think, okay? If the order of transaction isn't clear, someone might appear to spend the same money twice, that is double spending attack, or might seem to have funds they don't actually have because they already spent those, double spending. So transaction validity always depends on what came before. That is why solving this ordering problem lies at the heart of the blockchain security, right? And in this slide, I've just explained you what Sybil attack is. We have T nodes as what do you say, as adversary controlled, n minus T, which are honest, and every party wants to uh, broadcast their transactions, publish some transactions. There's new transaction coming in by honest parties during various rounds. It may take some time for the transaction to travel on the network, round time. How can the parties agree which transaction happened first? And this question is the question crucial for security, because if a transaction did or didn't happen, a party may or may not have sufficient money, and transaction validity depends on past transaction. Double spend, the classic problem in digital money. I remember I've covered this before as well. So double spending is when someone tries to spend the same money more than once. For example, imagine I pay you with 1 Bitcoin and at the same time I try to send the same very Bitcoin to the other person. Clearly, both payments can't be valid. Only one payment is valid because I had the sum only for once. So how does the system handle this? On the deck, on the slide over there, you can see 3 rules out there, and we're going to see them. First rule of first seen. The oldest transaction is considered the correct one, and any newer attempt to the double spend is just rejected off, right? And then comes the second. If a node directly sees 2 conflicting transactions, meaning a clear double spend, right? It knows that at least one of them is malicious, so it goes and just rejects both of them because the person has done wrong, right? So let's just nullify both the transactions. This prevents an attacker from slipping through. And third, and very important, there's the idea of waiting for some confirmation time, say delta. If you wait for delta rounds and no double spend appears, then it's safe to accept the transaction. But if a double spend does show up within that window, both are rejected. And if a double spend shows up after the delta time, you just cancel out the second one and take in the first one because it has endured the time for the delta, right? So the waiting period is critical in practice. It's why, for example, in Bitcoin, you remember I was saying you have to stay in there for 6 confirmations. So yes, in Bitcoin, you often hear about waiting for 6 confirmations before considering a payment fail. Sorry, before considering a payment final. It's all about giving the network, enough time to reveal if any possible double spends are going to occur. Because if they occur outside of the confirmation window, we do not consider them. That is just nullified for us. But if it occurs within the confirmation window, both transactions are going to be failed out. Okay, when we talk about the blockchain ledger being secure, there are 2 core properties at its heart that it should satisfy that go by liveness and persistence. So let's start with liveness first. That means if I inject the transaction to the system, say I pay someone, then that transaction will eventually appear in the ledger of all the honest participants. I won't say all participants, I would rather choose all honest participants because my malicious nodes or my under the adversary nodes can behave in a very random way. So I want all my honest participants to have the same ledger. In other words, no valid transactions should get stuck in the limbo forever. Every honest node will eventually record all the transactions that have happened. So if I have paid out someone, I want all my honest nodes to have the transaction, to have that proof. Now the second property goes with persistence. Persistence does what? It actually guarantees consistency. If a transaction shows up in a particular position, say just position I in the ledger of one honest party, then it must also appear in the exact same position in the ledgers of all the honest parties. That is to say, the order should be maintained. It should be a reliable shared record of truth. The ledger, the shared ledger. So liveness, what it does, it makes sure all valid transactions get included, while persistence makes sure everyone agrees on the exact same history. So without liveness, the system might ignore the real transactions, and without persistence, different people could have different versions of history. Which would make digital money completely untrustworthy because I know something else, you know something else, and that story becomes whole wrong, right? For which every person knows a different story. So that is what I mean when I say that I want my ledger to have liveness, I want my ledger to be persistent. Now let's talk about the Garay Network Model, which is the framework that is used in a blockchain backbone theory. So this model first makes actually important assumptions that go by. First, the network is synchronous. That means if an honest party sends a message in round R, then all the other honest nodes are going to receive it by round R plus 1. And this gives us a clear timeline for message delivery. Second, the network is reliable. So even though an adversary might be very powerful, powerful than all my honest nodes, they cannot delete or they cannot drop the messages that are sent by the honest party. If an honest party sends the message, it could be delayed, whatever, but it has to reach but it has to reach all the other nodes. Third, the network is Sybil attackable. This means the adversary can eject as many fake messages in as they want, but they cannot delete or drop the messages that have been sent by the honest nodes. They can send different messages to different parties, true. They can also flood the system and try to confuse your participants, true, but they cannot delete in the nodes. And finally, parties do not have fixed or the pre-known identities. This means that the adversary can actually reshuffle the messages. From the perspective of an honest party, it may not be clear that who sent which message and when did they send that message, right? They only see the in stream of flowing data. In short, the Garay model balances both worlds. It assumes fairness, it assumes reliability, but it still leaves a lot of room for your adversarial behavior. And this mix is what makes it powerful for analyzing blockchain security, because we tell them that, okay, there is this place for blockchain security, and if there's a model that exists in theory, right, the model that can actually defy all of these, despite having so much room for adversarial attacks, if my model is actually able to prove that despite all this, the model is secure, it is actually secure for the real world. True? So we make all these assumptions that cyber attack is possible. We make the assumption that time is synchronous. We make the other two assumptions that say we do not have predefined identities. And there was one more, right? The second one, which I'm forgetting. The network is reliable. Even after all of that, if I say that, okay, my Garay model is going to sustain all of this and still be secure. And that means the model is going to stay secure in the real world, because when I'm giving my adversary all control, right? Still, then the model is proving itself to be secure. Then it has to be secure in the real world, right? So now let's just see how the model execution actually works in the blockchain backbone framework. And this is the last slide for this video lecture. If you have any doubts, any concerns, please make use of the comment section. Please make use of the G forms attached. And yeah, if you want any reclarification on the topics, or if you want clarification on the topics that I could have unintentionally missed, just let me know of those as well. So yeah, now let's see how the model execution actually works in the blockchain framework. Every participant in your system is modeled as an interactive Turing machine. And when I talk of Turing machine, just think about processing inputs, maintaining memories, giving out outputs. That is it for the Turing machine that you have to keep in mind right now. It's not TOC, you don't need to know much more. When I talk about Turing machine, just know that processing inputs, maintaining memories, sending outputs. That's it. So the execution itself is coordinated by a special probabilistic polynomial time Turing machine that again goes by PPT-TM, and this is called the environment, this is called Z. So you can think of it as the conductor of the whole system. So Z captures the notion of rounds. In each round, it does the following. It invokes every honest party, giving them all the network messages they received in the previous round, because round R messages are going to reach by round R plus 1. And once that's done, then the environment invokes the adversary. The adversary is what we call a rushing adversary. And why do we call it a rushing adversary? Because it gets to see all the honest party messages before deciding how to interfere. So the adversary can then reorder the honest messages, inject fake ones to simulate cyber attacks. But what it cannot do is to remove or is to delete messages. So honest communication always gets through, sometimes mixed up with the fake messages, mixed up with the junk messages. And it can possibly, because of all this, get delayed, get disguised, get surrounded by the noise, but it will always be there. It cannot be deleted. So finally, these modified messages are what honest parties are going to see in the upcoming round. Throughout this process, parties are allowed to keep their local state. Because I need to know what is my history, right? They are going to remember their past messages, they're going to remember the past decisions, which is actually critical for maintaining a consistent ledger. So, in short, what happens? Your environment is going to drive the rounds, the parties are going to act according to the state, and the adversary is trying to disrupt things within the allowed rules. That is why this is a security proof model, and this is what has been proved by Garay's model. And it's not a deployment system. So in practice, honesty is unknown. The environment is never going to know which are honest nodes, which are fake nodes, which are which are adversary control nodes, I would say rather. But in proof, we assume worst case. An adversary controls T parties, and if still we can guarantee properties like liveness, we can still guarantee persistence, we say it is going to hold true in the real world as well. So that is it. It is just, a security proof model. I won't say it's a deployment system. So now you know what is actually this model. It actually is a model that is going to prove your security. That hey, if I have n nodes, I have t nodes as adversary controlled, still my model is robust. Still my blockchain model is robust. And this is what is actually proven through this model. So yeah, if you like the video, if you were able to understand the concept, just go in, like the video, subscribe to the channel, and with yeah, I'll take your leave. Thank you so much. Bye bye.